Large language models have a hard cutoff date. Once their training weights are set, their internal knowledge is frozen. To track a new discovery or a live market fluctuation, you have to retrain the entire model.
Beyond every horizon lies a new frontier. Explore, build, evolve. AuraLith Frontier.
Retrieval-Augmented Generation, or RAG, bypassed this by giving models access to dynamic external databases. It lets them read new information on the fly without changing their core weights. This diagram shows traditional RAG's three pillars: a knowledge base, retrieval, and generation. The system breaks documents into chunks, converts them to numeric embeddings, searches the vector database, and appends those chunks to the prompt for the model's final response. This process is highly efficient, but it is entirely passive. Traditional RAG is essentially a search engine integrated with a text generator. This linear flow handles simple trivia well, but it struggles with complex business logic. Consider a query asking for a comparison of quarterly market data across 3 global regions, while accounting for seasonal supply chain shifts. Traditional RAG chunks and embeds text based on semantic overlap, matching words that are similar to the query, rather than how the ideas logically connect. The basic vector search queries the database and returns isolated facts that share similar vocabulary, but lack structural relationship. The language model receives this fragmented context. It tries to synthesize a complete picture from shattered pieces, often resulting in a shallow summary or fabricated details meant to bridge the logical gaps. As enterprise needs move from simple retrieval to multi-step reasoning, this linear structure reaches a logical dead end. The first failure point is scale. As a vector database grows to millions of tokens, finding the exact nearest neighbor to a query becomes computationally intensive. This scale triggers a geometric problem known as the curse of dimensionality. In low-dimensional spaces, similar concepts cluster together, but as data expands into hundreds of dimensions, a phenomenon called distance concentration forces data points outward. They form a shell where every point is roughly the same distance from the center. Mathematically, the ratio of the distances between the nearest and farthest neighbors to any query approaches 1. This means the system cannot distinguish between a highly relevant text chunk and a completely irrelevant one. To the search algorithm, they look identical. Engineers apply workarounds to maintain speed, using approximate nearest neighbor methods like HNSW graphs or locality-sensitive hashing. These approximations force a trade-off. You sacrifice search accuracy for speed, and you handicap the system's ability to update dynamic indexes in real time. Scaling up a vector database leads to diminishing returns. To solve complex queries, the underlying architecture must change. Beyond the math, standard RAG faces a logic bottleneck. Queries often involve abstract concepts or temporal shifts that require deep historical context. Standard semantic text chunks are flat. They record vocabulary, but they cannot capture hierarchical relationships or dependencies between ideas. GraphRAG provides a structural solution to this by reorganizing these flat chunks into a relational map. In this architecture, a language model reads unstructured text beforehand, extracting and labeling structured data points. It replaces flat vector storage with a knowledge graph, a web of concepts called nodes, connected by defined logical pathways called edges. This structure enables semantic aggregation. When asked an abstract question, the system traverses these pathways, following logic from node to form a complete answer. While GraphRAG maps context, it is still a single-pass retrieval system. It pulls data once and generates an answer, lacking internal mechanisms for self-correction. There is an inherent risk in a model providing a final answer in a single, unverified attempt, particularly when accuracy is critical. SelfRAG addresses this by building an evaluation loop directly into the generation phase. The process moves through 3 phases. The model generates a draft, critiques its own output against the retrieved data, and refines the response before finalizing it. This iterative self-reflection catches hallucinations. It rejects inaccurate claims during the critique phase, improving the final objective accuracy. Self-reflection improves the output, but the system is still limited by the initial retrieval. If the first search is incomplete, the model is simply refining a partial picture. The final shift decouples retrieval from its status as a single passive turn. This is Agentic RAG. It operates on the React framework, reason and act, moving the AI from a generator to an autonomous agent. The language model now functions as a dynamic router and planner, determining how and where to find the necessary answers. We can modify the standard RAG flowchart. The static retrieve box is replaced by a central agent router hub, connected to a network of specialized tools. For a multi-step query, the agent plans a route and decides to query a vector database first. Realizing it is missing numerical context, the agent takes an active step, reaching out to a live API or a calculator tool to fill the gap. It then cross-references that new data against a knowledge graph for self-validation, iterating until the complete answer is assembled. Agentic RAG functions as a multi-source orchestration engine, replacing the blind fetching of earlier models. Engineering teams must choose between these architectures based on the logic their use case requires. This cable from the CSIC 2024 Literature Review compares iterative refinement and structured knowledge. Self-RAG provides high self-improvement and adaptive reasoning. GraphRAG focuses on high reasoning capability through structured knowledge representation. We can add Agentic RAG to this comparison. Agentic RAG handles dynamic, data-intensive tasks that require the simultaneous analysis of multiple live data streams. While GraphRAG struggles to update its nodes for rapidly changing data, Agentic RAG is built to process it. There is no single architecture that fits all needs. The correct solution is dictated by the complexity and the velocity of the data. These advanced systems involve trade-offs. Multi-step retrievals and feedback loops increase cumulative latency. They also introduce coordination complexity. If one sub-agent fails to pull the correct data, the entire loop can stall. Despite these costs, AI design is shifting from passive pipelines towards active, self-governing networks. Systems now navigate, analyze, and reason through the data they access. Linear RAG fetches data. Agentic RAG applies it.
The journey doesn't end here. See you at the next frontier. AuraLith Frontier.